Welcome back, everyone. Hope you had a good spring break. Let's see, what did I do? Let's go with the learning schedule. So just a few minutes to get us updated, and we'll get you back to working on things. While you can use late passes for previous assignments, the older they are, the late pass only brings it up, I don't know, maybe 72 hours or something. So an older one, you might have to use multiple late passes. What I've done, anything from the first exam, I took off the due date, which means you can get freely into those. So if you hadn't finished those and you want to finish those up, you can do those at any time. There's no longer a due date. You won't need a late pass. And those will help you as we get ready, as we move towards the final. So someone contacted me, said they got all of this stuff for the second test done over spring break, which was great, but then they wanted to go back and they were having problems with the late passes. They do it and it would take their late pass, but then they couldn't work on it. I said, I remember someone told me like they needed 10 late passes on an assignment one time. So this way it'll smooth anything. You can go back and work on anything you didn't finish up before. Remember, if you get into review mode, it won't give you points. It'll just let you review, but you can contact me. I have a way I can clear that review mode. I don't know why they don't let you clear it, but anyway, I can clear it for you, and I did that a couple times, so keep you moving. Where we should be, we had our spring break, no classes, so we're at 6.1 and 6.2. Rational functions, and I'm going to do just a little brief review on the difference, what happens with rational functions, because there's a fraction, there's a top and the bottom, and the top does something different than the bottom does, so we'll kind of get just a brief thing over there. There's some graphing, and then next week we will go into full review mode. And currently the only review I have, which last time worked out, is from last semester, so as you finish up through chapter 6, let's see, where is it? Yeah, second exam content. Where did I put it? I thought I had a whole, maybe it's just here. Let's see, let's click here. Yes, so there are PDF files with the review itself, the key, or answers to the questions, and again, remember, it's some of them are fairly detailed. And then I do have some solution videos, I think through 19, and this week I will work through getting some additional. I think I've actually got some additional ones that I did for the final. I'll get those posted here, but we'll get, because there's what, 30 or 40 or maybe 50 questions in there, we'll get them all. But working through them is the best preparation. I do not have a copy of the test, what the test will be yet. Hopefully that will appear sometime by the weekend at the latest, because they're rewriting them. And when I get it, I will get you to focus. I'll say which ones you really need to focus on, okay? But for right now, do as many as you can. They'll all be helpful, but I'll get you specific ones that, hey, there's gonna be one like this on the test, so please do it so that you understand it. So that's where we're at for this week, next week, and so next Thursday's when we take the test again. And again, it'll be 20 questions like last time, multiple choice like last time. So all you have to do is choose the right answer, right? So we give you all the answers, we just mix them in with a bunch of wrong answers. So your goal is to choose out the right answer. And again, there's some pretty good wrong answers that are, that's why they call them distractors. Sometimes I think they're too good. But anyway, that's where we're at. So let me see how it's. I guess okay, yeah, I do it with Word. See, I go to spring break and I forget how I use all my tools. So I'll use Word real quick. And again, this will be maybe a 5 or, yeah, we'll keep it to about 5 minutes on rational functions. Okay. So rational function is a fractional function, something in the top and something in the bottom. And when I say something, it's more than just a number, right? It's got variables in both parts, at least in the bottom part. So if there's just a number in the bottom, we don't call that a rational function, but it needs a variable in the top, specifically the bottom. Sometimes we could have like 1 over x, and we do call that a rational function, okay? So it doesn't have to have one in the top, but oftentimes it does. So here's what happens. What if we divide by something by 0, what happens? Anyone got a calculator out? Take 1 divided by 0. Yes? It's undefined. What does that mean, though? That's not really helpful, right? It's just undefined. It means it doesn't exist. What does it really mean? The way we get there is, let's see what happens. This is something called a limit as we get closer to 0. So what if I take 1 divided by 2? What would I get? 0.5 as a decimal. Okay. And watch, I'm going to get closer to 2. Or sorry, I'm going to get my denominator is going to get closer to 0. So I'll go 1 divided by 1. Right? Because 1 is closer to 0 than 2. Right? What do I get when I take 1 divided by 1? That's 1. Am I getting bigger or smaller? I'm getting bigger. I went from 0.5 to 1. Now, what happens if I were to divide by 0.5, which is smaller than 1, is closer to 0 than 1, right? If you put that in your calculator, it will tell you you get 2. I'm getting bigger, aren't I? What if I take 1 divided by 0.1, which is 1/10? Think of it, we're really just getting the reciprocal. This is actually equal to 10. So notice as I get closer to 0, my result is getting bigger, which we don't think of that as undefined, do we? But what happens is when we get, what's the biggest number we could get? What's the biggest number you could think of? The number that there is nothing any bigger than it. Infinity. But it's not really a number, it's a concept of, because you can never get there, right? Because if you got there, then, you'd be someplace, and then you couldn't get bigger, right? Infinity is this concept we can always get bigger. So that's why it's undefined. It's so big, it's beyond numbers, whatever that is. Okay, so I want you to get that concept though, because when we graph something, say 1 over x plus 5, what happens when x is actually at -5, right? Because if I put a -5, -5 plus 5 would give me 1 over 0. So over here at -5, the type of behavior we're going to get on something like this is that we're going to get what's called a vertical asymptote. And it would look, I think the graph will look something like this. And what you'll see is the graph is shooting off to either positive infinity or negative infinity, depending upon which side it's coming from. Okay, so that's what I want you to see, is that when we divide by 0, not only is it undefined, it's undefined because we're going to infinity. The y value is going to infinity. Okay, we call this and a lot of times we put a little dashed line over here because that's what's called a vertical asymptote, which is a Greek word, and I can never, something like that. There's a P in there. My spelling is not working this morning, so it's a Greek word that means to get close to, but basically not cross over, although sometimes you can, but basically really get close to that. So x can get very close to -5, but it can't exactly be -5 because that would get us to infinity, and we can't get to infinity. Infinity is a destination that we keep going towards. Okay, we get as close as we want, but we keep getting bigger and bigger. Okay, that's the idea. And the way we do that, because I've had a few questions on this, is we just take that denominator, set it equal to 0, and then solve for x. So that's why I could say if I subtract 5, when x equals -5, that's where it's going to be 0. That's where we're going to get a vertical asymptote. So a lot of these activities that you're going to be doing is finding asymptotes, vertical asymptotes. Okay, so that's all you got to do is take that all comes from the bottom. Notice I ignore the top. Doesn't matter what's in the top. It may be, well, except if you get 0 over 0, then that's a weird thing, and you'll deal with that in calculus. It's called the indeterminate form because it's, we need other tools to examine it. But that's a special case that we're not going to throw at you, okay? There's another type of asymptote, and that is, let me switch back, well, let me just, since we talked about the bottom, so if I have x plus 5 in the bottom and say I've got x minus 3 in the top, what's going to happen when the top becomes 0? And again, if I could see if I plug in positive 3 minus 3 is going to give me 0. It would give me some other number in the bottom, right? So let's just kind of say this was at x equals -3, plug it in, I'll get 0 in the top, but I'll get 8 in the bottom. What's 0 divided by 8? Good. That one is 0. So don't confuse that. That's not undefined. That is strictly 0. 0 divided by anything is still 0. Well, except 0 divided by 0. That's the thing we don't really know. So this is just 0. This is going to give us, so when the numerator equals 0, and again that would happen, oh wait, not at -3, at positive 3, sorry about that. X equals positive 3, I plug that in, I'm going to get 0, right? And then I'll get 8 down here. That's going to give us an x-intercept. Because we plug in positive 3, we get a y value of 0. That's an x-intercept. Okay, so what we know on this one, again, we could see we'll have an asymptote at -5, so we might get something like this, and then we're going to get it to cross at positive 3, so over here, so we might get, I don't know, something like that. The graphs, but we do know it's going to cross at positive 3, so that gives us an x-intercept. Okay, so when the top is 0, x-intercept. Okay, one more thing is horizontal asymptotes. Asymptotes, something like that. And that's going to be where the graph kind of goes to some horizontal in the long run. And so the graph, we could still have vertical asymptotes, right? And actually, let's take that let's take that one, x minus 3 over x plus 5. We know we're going to get a vertical asymptote at -5. But what happens with horizontal asymptotes is what's going to happen in the long run. Whenever we have a rational function, what's going to be the big part? So as x is getting really big, right, 1,000,000, is -3 a very important number in consideration of 1,000,000? 1,000,000 minus 3 is still pretty close to 1,000,000, right? 1,000,000 plus 5, still pretty close to 1,000,000. So what happens is when we're looking for horizontal asymptotes, this is called, you'll see it in the lessons, called long range or long-term behavior. So what's happening when x is getting out towards the ends of the graph, infinities, right? Positive infinity over here, negative infinity over here. We'll get a horizontal asymptote, and the way we can find that is we just take the largest terms, the largest degrees, so this is x over x. We can ignore anything else, and what does x over x become? 1 over 1, which is 1, and so we'll see that we also get a horizontal asymptote here at y equals 1. And so what that would look like is the graph would be something maybe like this, where you'll see that long behavior. Now, because we've got this x-intercept, it actually probably would like come down here. And I don't, again, we'd have to graph this to see what it is, but long-term behavior is going to go to that. So the asymptote, and there are 3 cases. Okay, so let me see. Okay, 3 cases. So there's where the degrees are equal. Let's do this. So I'll go with maybe 3x to the third plus 2x squared minus 4 in the top, 9x to the third minus 5 in the bottom. On this one, for horizontal asymptotes, all we have to do is consider the degrees that have the highest, both on the top and the bottom. So would you agree that the degree is the exponent, so the exponent of 3 is the biggest? So we can treat this, we basically can ignore everything else. And so this becomes like 3x to the third over 9x to the third. The x's are going to cancel each other out, right? Because they're the same number. So this is going to behave like 3 over 9, which is 1/3. So what that means is we'll have a horizontal asymptote at y equals 1/3. Okay, so that's one case. Whenever they are, so notice it's just the ratio of the coefficients. So that's first case. Second case, the top is bigger than the bottom. So something like 5x to the 6th over 2x to the 3rd plus stuff, right? And again, it doesn't matter what the stuff is, we're only focusing on the biggest degrees. What's going to happen is we just take these 2 biggest degrees and do the same thing. 5 over x to the 6th, 2 over x to the 3rd. We can reduce this as a fraction, right? X to the 3rd, we can subtract exponents. The top becomes not x to the 6th, but x to the 3rd, because 6 minus 3, right? 6 minus 3, that's that. So we end up with 5x to the 3rd over 2. And when x gets really big, what's going to happen to this? It's going to get really big, right? Because it's all in the top. And then we divide it in half. So what is an infinity divided in half? Sort of still infinity. So this one has no horizontal asymptote. Yes, I think there's a y in there somewhere. Okay? So when the top is bigger, it's just going to go off to infinity some way. And again, the easiest way to do is actually go ahead and graph these. You can actually see these happening. And so there's one other thing that happens, and can anyone guess what that's going to be? We got they're equal, the top's bigger, the bottom's bigger, right? And so that we could just flip this. If we had 2x to the 3rd over 5x to the 6th, again, when we subtract the exponents, it ends up in the denominator, so this reduces down to 2 over 5x to the 3rd. Okay, and so what happens as x gets really big, this is going to behave like 2, basically x to the 3rd goes to infinity, 5 times infinity, a really big number. So what happens when we divide by a big number? The opposite of what happens when we divide by 0. Remember, division by 0 goes to infinity. So division by infinity actually goes to 0. So this is going to have a horizontal, and again, you'll see this on a graph. What happens is, it goes to 0 somehow, maybe like, you'll see it. So this will have a horizontal asymptote at y equals 0. Okay, so those are the 3 cases. You'll pick that up in the lessons, but I just wanted to kind of make that explicit. So vertical asymptotes whenever the bottom gets 0, x-intercepts whenever the top is 0, and then to find a horizontal asymptotes, we look at the ratio of the top to the bottom. Okay, and then there's 3 cases. If they're equal, it will go to whatever the ratio of their coefficients is. If the top's bigger, there is no horizontal asymptote. It goes off to infinity or negative infinity. And if the bottom is bigger, there'll be a horizontal asymptote at y equals 0, the x-axis, right? That's what y equals 0 is, it's the x-axis. And that should give you a good start through most of what you'll be doing in